What we're going to do tonight is something that Sandy and I joke about. Sandy's sort of the butt of the joke sometimes, is we try to cover ancient history up to the present, and so I take the last 100 million years and Sandy takes the last 100. And he has a hard part, because as we've learned in various expeditions we've taken, lots of the old record doesn't exist anymore, but Sandy can't very well leave out much of the last 100 years, so he has a lot of time to explain. So what we're going to do, the title is From the Cretaceous to the Coastal Commission. Does the Cretaceous mean something to everybody? It's sort of right after the Jurassic, so we could have had Cretaceous Park, but something about Jurassic Park sounded better. So we're going to talk about Cretaceous Park, but the link to the Cretaceous, which is sort of the oldest stuff we have in Santa Cruz County, what I want to do is kind of go from the oldest to the most recent, is stuff we don't really know how old it is. I'm just calling it the Cretaceous because I like the sound of the word. But we know it's about 100 million years or so old, and that's also the time when the dinosaurs were still around. At the end of the Cretaceous, we had a large event take place that we now understand probably led to the extinction of the dinosaurs. As I started thinking about the Cretaceous and dinosaurs, I started thinking about, well, gosh, were there dinosaurs in Santa Cruz County? Were there dinosaurs in California? And fortunately, I ran into a person this afternoon who studies dinosaurs, and I got the answer to that question. And it turns out, although people haven't known that for a long time, there are dinosaur fossils in California, and they're scattered down in the Panoche Hills. There's some in Marin County, and it turns out they're sort of scattered around the margins of the Great Valley, the San Joaquin-Sacramento Valley. And they follow, well, they're what we call ankylosauruses, which were these spiny plated things that were all very heavy on the top with all these big spines, and they're buried in marine sediments, even though they were all terrestrial dinosaurs. And I asked this person how to explain that. He said, well, it's called the bloat and float hypothesis. And what that means is they died, they lived around the margins of this, what was then a sea, along the rivers, along the coastline. When they died, they tend to bloat. And if they fell in the water in the river, they tended to float. And so they floated off into these marine environments and then sank and were deposited in marine sediments, even though they were terrestrial animals. And one of the ways they know that is whenever they find these things, they're all laying upside down with their feet up with these heavy plates down. What I want to do is just kind of work our way up from the past to the present, leaving the last 100 years for Sandy. And now that I've explained that we do have dinosaurs in California and about the Cretaceous, and that's about the oldest thing we have in California. But I'm going to try to look at a global perspective first, and then come into sort of a regional perspective, and then a Monterey Bay perspective, and then we'll end up at the Marine Lab, so you'll know where I'm going tonight. And something that I've talked about many times, and you've probably all heard many times, is until perhaps the 1960s, we had a somewhat different view of the Earth than we do today. And now, in the 50s and 60s, we began to discover for the first time that, in fact, the ocean bottom had features on it that were very different than what we expected. There were ridges, there were trenches, there were volcanoes, and that began to tell us sort of how the Earth went together and how it sort of came apart. One of the big clues was the distribution of earthquakes, which began to define a series of plates on the Earth's surface. And that began to tell us a bit about why we had things like the San Andreas Fault, why we had things like the Aleutian Trench and the Peru and the Middle America Trench and the volcanoes of all the way around the Pacific Basin. So we now realize that the Earth consisted of a number of large rigid plates that moved around relative to one another. Where plates came together, one of three things had to happen. We could either create new ocean crust or new continental crust, and plates would move away from each other. But if that happened someplace else, they had to come back together so we wouldn't make the Earth larger. So we have trenches or subduction zones where plates go down, which happens all the way along the margin of South America and Central America, and actually almost all the way around the Pacific we have these trenches. When that material goes down and melts, it comes back up as volcanoes, so we have volcanoes and the Cascades and the Aleutians in Japan and the Philippines and New Zealand. So plates could come apart, they could come together, or they could slide alongside of one another, and that gave us something like the San Andreas Fault. And if you look at the terrain or the relief of the U.S., it really reflects its tectonic history. On the one hand, the West Coast is very rugged. It's been a place where plates have collided. We have a long history of collision between what's now out in the Pacific and what's North America. It's created the Coast Ranges, the Sierras, the Rocky Mountains, and I'd prefer to say that that's sort of young and active. On the other hand, once you get to this side of the country, there's really not much there, geologically speaking. I don't even know about the baseball teams back there. So the terrain is older, it's flat, it's subdued. I mean, some people call these mountains, but in the big scheme of things, they're pretty small. So I'm going to call that side old and boring. And if you look at the continental margin or the edge of the coastline, the East Coast we call a passive margin or a trailing edge because it's sort of trailing along behind North America as it collides with the Pacific. It's been there for a couple of 100 million years. The mountains have been worn down. We have barrier islands, bays. There's almost no relief on the East Coast. In fact, the highest point in Florida is at Disney World, and it's now, it used to be Epcot Center, and now it's a new Mount Everest. It's, I don't know, 150 feet above sea level. On the other hand, we don't really have much like this on the West Coast, but we have a very different kind of margin. So we can look at New Zealand, we can look at Alaska, and we call these collision margins, leading edges, where plates are colliding, they're pushing up mountain ranges, volcanoes are forming. So it's a much more active, sort of vibrant, geologically young landscape. We also have sea cliffs. We have steep coastal mountains, again, very different than the East Coast, because these are forming today. The coastline in Santa Cruz is still coming up at perhaps 0.5 millimeter per year. On the East Coast, it's sort of sinking and wearing away. And we also have one of the best indications of collision and uplift, which are these marine terraces that really characterize Santa Cruz. These are all former seafloors that are being elevated as plates are grinding alongside of one another or pushing against one another. For many millions of years, the Pacific plate was colliding with the North American plate, and that created a lot of the topography we see, things like the Sierra Nevadas and the Coast Ranges. About 20 million years ago, that all changed, and in fact, due to larger scale plate motion, instead of a collision, the plates started to slide alongside of one another. So about 20 million years ago, we had a major change in plate motion. And if we look at a blow-up, we'll see the Central Coast. And even though we think about a single feature, the San Andreas Fault, in fact, if you realize we've got all of North America clear out to the middle of the Atlantic, and all the way over to Japan, moving alongside of one another, it's going to be more than a little hairline crack in the Earth's surface. In fact, it's a zone that might be 30 or 40 or 50 miles wide. So while we have the San Andreas Fault, we have the San Gregorio-Hoskree fault system, we have the Calaveras, the Hayward, there's a whole zone. We're kind of caught in a vice here. In fact, the Loma Prieta earthquake was an indication of that continued movement of North America beside the Pacific plate at about 1.5 inches a year. And again, Loma Prieta was a reminder that we are in a seismically active area. In fact, there are hundreds of earthquakes on the Central Coast every day, most of which we don't feel. One of the things that we rely on as geologists is something called uniformitarianism. It's sort of a made-up word, but it works. And the idea behind that is that the things we see happening today are good indications of what happened in the past, so that in fact, if we go over to Arizona and see these large bedded sandstones in the Arizona, Nevada area, we call the Navajo sandstones, you see these huge preserved, what we call crossbeds. In fact, they're exactly what happened in sand dunes today as they form. So we can say, if we see these kind of features in the rocks, we can look at today's processes and get a good idea of how those things form. So we can look at things like grain size, the material. Do we have big cobbles? Do we have pebbles? Do we have sand? Do we have silt or clay? We can look at the grains and whether they're rounded or smooth or angular, and we can look at the fossils. we can look at the structures in the rocks. And that's what we do as we sort of do a autopsy on the Santa Cruz Mountains and look to see how would these things have formed if we can look out in the present ocean and see what's happening today. So these are the things that give us a clue as to what the history of the area is and where these things were deposited. Now, in contrast to uniformitarianism is another concept called catastrophism. And for years and years, we thought everything just happened very uniformly over time. There are some other events, however, that alter that perception. In fact, it's been said that the history of the earth is like the life of a soldier, long periods of boredom separated by short intervals of violence. So that in fact, we can go on for tens of years or hundreds of years, maybe even millions of years, and then we have a major event. Mount St. Helens erupting, or 65 million years ago, when an asteroid hit on the Yucatan Peninsula or in the ocean, and a lot of good evidence suggests that that was the factor that created the extinction of the dinosaurs from nuclear winter and stuff in the atmosphere and so forth. So that is definitely a catastrophic event, and it's nothing very uniform, but in fact that tells us about some of the interruptions in this normal sort of day-to-day process. So if we were to look at the Santa Cruz coast landscape here, and this is a cross-section drawn many years ago. If we were to look at the Marine Lab, it'd be sitting down here. And this is sort of just like taking a paper cutter and going down through the Santa Cruz Mountains, right up through the university, up to Empire Grade, and out here on the coast. Here's Highway 1, and Davenport's up here someplace. We could look and see at the core, under the Santa Cruz Mountains, which is what you'd see if you go up onto the campus or up Empire Grade, you'd see a couple of things. You see marble. And marble is actually the building block for cement that keeps the Davenport cement plant going. You'd also see granite. So those are the two oldest materials we see in the Santa Cruz Mountains. And in fact, because the marble is enclosed within the granite, we know it was incorporated into it as that molten rock rose within the earth crust. So we don't know exactly how old the marble is because there's no fossils that are still preserved and there's no way we can date it. But a good guess based on how it interrelates with other materials is probably the Cretaceous. It could be even a little older, maybe the Jurassic. But it's the oldest material we see in Santa Cruz County. And in fact, as I say, that's what we've been shipping up to the cement plant in Davenport for many, many years. It's the building block for Portland cement. Well, how does marble form? Well, if we look at it sort of historically, it takes a lot of very, very small microfossils that consist of calcium carbonate. Things like coccoliths, things like foraminifera, billions and billions of those that form, live and die in the ocean. Something like 100 million years ago, those die, sink to the bottom, and when they are deposited in thick enough volumes, we actually start to create sort of a calcium carbonate mud. Over time, that will form a limestone, but if we expose the limestone to increased temperature and pressure, we actually recrystallize all those fossils and create marble. We can have what we have in the Santa Cruz Mountains, very coarse-grained marble, and we can have what Michelangelo carved, which is a very fine-grained marble. That has to do with the pressure and the temperature and the crystals that grew. So this is the oldest stuff around, about 100 million years old. One of the questions that Sandy will ask is, if the Earth is 4.5 or 4.6 billion years old, how come the oldest stuff in Santa Cruz is only 100 million? What happened to the other 4.5 billion years? And I'm sorry, Sandy, we lost that. We don't have it here. So geologists can do that. You just move things around, put them someplace else. In fact, it's very hard to find the oldest rocks on Earth because they've been recycled so many times. They're recycling like billions of years ago. We just push it back in the earth and heat it up and it converts to something else. So we have to go to places like Labrador and Newfoundland and Australia to find rocks that are even up into 3 billion years old. And the only reason we really know how old the Earth is because we went to the moon and dated the moon, to thoroughly confuse you. So the marble is contained within granite. We've got granite out at Point Lobos. We've got granite up off of Old San Jose Road in the Alice Springs Quarry. And we actually can date the granite with potassium-argon dating, and it's about 70 million years old, plus or minus. So that's the oldest stuff we can actually date. And if we look at a geologic map of California, it's sort of color-coded here, paint by the numbers. The red is the Sierra Nevada. The blue is some of the volcanic stuff on top of it. But this is the granite of the Sierra Nevada. And what you see, here's the San Andreas Fault. And you see the Sierra Nevada granite kind of comes down into the fault zone, but it's been all kind of broken up in here. And if we look along the fault zone in California, we've taken that granite, and as this side of the plate or fault has moved northward relative to this side, we've stretched that granite out through California. So all these little areas of red, this would be the Logan Quarry out along Highway 152? No. Chittenden Pass, 129. We've got Point Lobos, we've got the granite under Empire Grade, we've got Montara, the Farallones are actually granite, and finally up at Bodega. So those are all spots of Sierran granite that have been moved north 300 or 400 miles over the last 20 million years. So what it shows us is all of this part of California is moving northwest, and the granite is sort of a piece we can tie back to the Sierras, moving about 1.5 inches a year. So if we go back to this cross-section through the Santa Cruz Mountains again, sort of lapping on top of this like a bunch of pages in a book, which they are sort of geologically, are a whole series of sedimentary rocks that formed underwater for the most part. And there's one other law, principle in geology called the law of superposition. And what that means is, in a normal sequence of things, if we're depositing sediment on the seafloor or in a lake, we'll deposit one layer, and over time more sediment will be deposited on top of it. Sort of you read a book from front to back. So that the deepest stuff at the bottom should be the oldest. And the only problem with that is there are times when those layered sedimentary rocks get bent completely up on end. So as you go over Highway 17 right at the summit, you'll see the layers that are on end, which means, well, was it this way or was it that way? In fact, if you get up into the Alps, you'll see that as North Africa crashed into the Mediterranean and Europe, the Alps have actually been bent over double in several places. So you have to be kind of careful at how you unfold those to keep things in the right position. But importantly, we don't see any Lompico sandstone out on the coast, so I'm going to leave that out. That's up in the valley. But we do see the Monterey Shale, which is one of the oldest units, one of the oldest sedimentary units. And sitting on top of that is something we call the Santa Margarita Sandstone. So if we were to look at the Monterey Shale, it has an interesting history. The Monterey Shale actually underlies Love Creek. And if those of you that were here in 1983, 82, remember the 100-year rainstorm and the flooding and so forth. And the Monterey Shale up in the San Lorenzo Valley has actually been folded up to a slope. And the angle of that slope is about 30 degrees. So the shale is very impermeable. It's almost like a concrete driveway. This is a look at the head of the Love Creek slide. In fact, 200,000 or 300,000 cubic yards of soil and trees and weathered rock moved down on this sort of concrete ramp because it was completely saturated after about 30 or 40 inches of rain in November, December, and then 17 inches of rain in 28 hours. So it sort of floated that material up as mud, came down the hill, buried 9 houses and 10 people that were never recovered. And this is one of the houses that was left at the bottom of Love Creek. So it occurs up in the mountains. We also see it along the coast. This is up at Año Nuevo. If you go on one of the walks out there, you'll see there's Monterey Shale. It also happens to be one of California's major oil producers. It's about 20 million years old, plus or minus 20. Nah. It's really hard to put an exact date because it covers a range of time, so maybe 15, 18, 20, 21, 22 million years old. Sorry, Sandy, it just covers a lot of time. So one of the things to ask ourselves, if we go back to uniformitarianism, is if we were to look at shale today with oil in it, where would that form? So what would this area have been like? Just like we knew there was limestone, which meant this had to be an ocean. This had to be a fairly deep ocean back in the Cretaceous. You know, it It wasn't terrestrial. To form the marble, we needed the limestone, we needed those plankton. So this had to be an ocean for that period of time. Back in the Miocene, 20 million years ago, we had an ocean environment here where shale was deposited, or actually clay, and oil formed. So if we looked at the offshore area today, here's Monterey Bay, sort of a oblique view and looking offshore. This would be Marine Lab out about here. You know, where would you have that happen? Well, it wasn't in a river, it wasn't right along the coastline, but it was probably offshore in some basin where all the sand and silt had been left behind that came out of the rivers, and it's the fine-grained clay, it's sort of the mud in the water that's slowly settling down. But we also needed a lot of organic production. We needed a lot of plankton, things like microscopic algae, which are really the building blocks for oil. So what we know about that period of time is where we sit in the Santa Cruz Mountains today was also an ocean environment. This was all underwater 20 million years ago. If we look at the next geologic unit on top of that, we call it the Santa Margarita Sandstone, and most formations are named after where they're best exposed. So the Monterey Shale is in Monterey. I don't know where Santa Margarita is, someplace. What do we sort of think about when we think of the Santa Margarita? In Scotts Valley, it's known for sand dollars, it's known for shark's teeth. There's actually even some marine mammal fossils in there. There's a big deposit of it on Wilder Ranch. This is now sort of covered with trees, but they were quarrying that for many years. And much of Scotts Valley is underlain by the Santa Margarita Sandstone. So it's a very clean sandstone. In fact, Scotts Valley has this wonderful resource. It's one of their best aquifers. It's also where most of their wastewater goes into, and it's also good to quarry. So it's called multiple use, but two of those are degrading the first. In other words, it's hard if you're carrying it over Highway 17 in those semis every day and also pumping your sewage into it that you can still get your drinking water out of it. Did I make myself clear? So the Santa Margarita tells us we had a shallow sea. We went from the Monterey Formation that was fairly deep, clay was deposited, lots of organic productivity, up into probably something like a beach or a very nearshore environment where we see sand dollars, sharks. There's even a few surfers found? No. It's 16 million years old. We didn't have any surfers around. But we know this was sort of a shallow seaway that probably continued over into the Santa Clara Valley about 16 or so million years ago. So again, we're taking this concept of uniformitarianism. Where would you find a nice clean beach sand with sand dollars in it? Well, we'd find it along the shoreline of Monterey Bay today. So the water had gotten shallower from a few million years before. If we go back to this diagram again, now sitting on top of the Monterey Shale and the Santa Margarita Sandstone is the Santa Cruz Mudstone. That's sort of Santa Cruz's rock. That's sort of our pet rock, I guess. All of the stuff along the sea cliffs from West Cliff, from just about Elmore Avenue, all the way up to Davenport, all the way up almost to Waddell Bluffs, is Santa Cruz Mudstone. And when we say mudstone, it's a very hard rock, a lot of silica in it. In some places, it's almost like porcelain. Not many fossils. We find a few fish scales, but again, it's not sand, it's not silt. It's made out of mud or clay particles. So again, the water was deeper. This was an ocean environment 14 or so million years ago again. So it was deep, it got shallower, it got deeper again. And this is really quite thick. There's quite a few thousand feet of Santa Cruz mudstone that underlie much of the north coast. In fact, something unique about the mudstone, within it are something we call sandstone intrusions. Just like when hot volcanic material, lava, gets injected into rocks, we can actually create something called dikes, where these sort of tubes come up in the nearly vertical position, or we can have these that go in at a nearly horizontal position. We call those sills. Well, it doesn't have to be volcanic. We can in fact do this with soft sediment that we can liquefy, just like toothpaste. So we believe that under the mudstone, perhaps from the Santa Margarita Sandstone, but it could have been from even lower, we actually liquefied that sand. And if you go up the coast to many of the North Coast beaches, you'll find these dikes and sills. In fact, this one, you can just see it in the cliff here. The reason that tunnel is there is because that was a site where the waves could remove that softer material. In fact, a lot of the arches and the tunnels and the caves along the Santa Cruz coast were created where these intrusions were weathered out. In fact, if you go to Yellowbank Beach or Panther Beach, which is about 6 miles north of town, you'll see this whole cliff about 600 feet across is one massive sort of funnel-shaped intrusion that was squeezed up perhaps during an earthquake when water-saturated sand was liquefied, just like happened in 1989. We shake this, the grains lose contact, they're saturated with fluid, it turns into a paste, and it got injected because of the squeezing of the overburden up into the materials, and we created these really bizarre structures. And in another case, up between Majors and Laguna Creek on Back Ranch Road, we find that some of that sand was saturated with oil. So it was a fluid that allowed it to liquefy, but in fact there are a number of asphalt quarries that characterize this part of the coast for the first part at least of the 20th century. This was actually used to make asphalt, natural asphalt with it. They took up to San Francisco after the earthquake and actually made tiles and so forth with it. So it's another indication of an earlier period of time that's much different than what we see today. Sitting on top, about the youngest stuff we see around here, is the Purissima Formation, and that begins to appear about a mile south of here. By the time you get to Lighthouse Point, all the way through East Cliff, Capitola, New Brighton Beach, down to Aptos, is the Purissima Formation. It's very sandy, and I think probably everybody in Santa Cruz has a rock that looks like this somewhere on your doorstep. Well, you all broke the law. Now, it's okay, you can take that. There's a lot of it around. There's also, out in front of the Seymour Center, over where the whale is, you'll see some big chunks of rock that have whale bones in them that came out of the Purissima. So in fact, we know it was also a marine environment. Where would you expect to find something like this forming today? This sort of shell hash, you know, lots of pelecypods and mollusks. Well, I think probably something like an Elkhorn Slough, maybe something like a San Francisco Bay, a shallow, perhaps an estuary, maybe a marine environment, but somewhat protected with a lot of marine life, a lot of shellfish, and in fact also whales that wandered through and somehow got stuck in there. So we have up to perhaps a few million years ago, one of the features that characterize the very recent time are these marine terraces. So we're sitting down here tonight, and we see this very flat bench that most of Santa Cruz is built on. If you go up the coast a few miles or even follow Bay Street up towards the university, you'll see there's a lowest terrace that most of the west side is built on that's about 125,000 years old. There's a second terrace, a third terrace, a fourth terrace. In fact, in part of Bonnie Doon, there's actually 5 terraces. Well, how did these form? Why do we have these stair steps going up the Santa Cruz Mountains? Well, it's related to 2 somewhat different processes. One is, over time, over geologic time, temperature has constantly been changing. So this is going back from the present, 0. We have a very warm period. This is sort of temperature change. This is going back in time to about 120, 160,000 years ago. So temperature has changed, and that has to do with how far we are away from the sun. As it gets warm, the glaciers and ice packs melt, the runoff goes into the ocean, and sea level rises. When it gets cool, and this is the same pattern going back about 150,000 years as we showed here, but this is temperature, but it also reflects sea level. So in fact, when it's warm, the glaciers melt, sea level rises. When it's cold, we sequester ocean water as rainfall onto the continent, sea level drops. So through geologic time, sea level is constantly changing on the order of 5, 10, 20,000 years. What that means is, even though we have built an entire civilization virtually at sea level, the ocean is never at one point for more than a few hundred years. There's now 100 million people living within 3 feet of sea level. None of you, I'm sure. Which means if sea level continues to rise, which is very likely because of global warming, we're going to have a problem. So one of the factors that gives rise to these uplifted marine terraces is that sea level is constantly rising and falling. When sea level is high, like it is today, the waves are scouring away at the cliffs and creating a wave-cut platform. At the same time, however, the coastline is slowly rising. So if we now go into a cool period and sea level starts to drop, what's going to happen is the coastline is going to continue to rise, sea level is going to drop. The next time it gets warm, sea level starts to rise. It comes up to about the same elevation, but now we've raised the land 50 or 100 feet above that. So it's a mixture of constant sea level change and a slowly rising coastline, which gives us these terraces, which really make Brussels sprouts possible. So if we go back and look offshore, we can find the edge of the continental shelf off of Santa Cruz or off any continent is really the low stand of sea level from about 120,000 years ago. So we know sea level, I shouldn't say 120,000, about 20,000 years ago, this is where the coastline was. Sea level was about 350 feet lower than it is today. So as the ice melted, the last ice age ended, all that water flowed into the ocean basins and sea level advanced up against the continent. So all this real estate, have any real estate agents here tonight? It's all gone. Not only that, we're going to lose some more. Okay. So I'm going to intrude a little bit on Sandy's territory the last couple hundred years. And what I wanted to tell you basically is even within the last 25 years of Law and Marine Lab, the last 35 years that I've been in Santa Cruz, there's been some major environmental changes. I think as we look around today, coastal preservation, the Coastal Commission, the sanctuary, we get a feeling that we've really been, we've really been careful, we've protected the coast, we've taken care of our resources, but that is a very recent phenomena. And if we go back to 1969, Pacific Gas and Electric came into Santa Cruz and proposed what was going to be the world's largest nuclear power plant at Davenport. Some of you may have been here, some of you may know that, some of you may not. They were going to build 6 1-million kilowatt reactors to supply our growing electrical need. Needless to say, they were also going to build one at Point Arena, Bodega Head, Moss Landing, Malibu Canyon, and Seal Beach that were never built. So I want to thank you for all your energy conservation. But this was a big issue for Santa Cruz back in 1969. I think the first issue was, wow, that's really going to increase our tax base. We'll have these great schools, these great radioactive schools. So a citizens group formed and opposition appeared and geology came into the issue and so forth. And now that coastland and Dairies property was recently taken over and is now public property. At the same time, if you were to look at Davenport across the road from the cash store, and again, I'm not blaming anybody, this is just a different mentality. Back in 1969, the city of Davenport simply took all their garbage and trash across, dumped it on the beach, and every once in a while they just lit it on fire. So that was the city dump for Davenport. The North Coast, what is now Wilder Ranch, was bought by a Canadian investment firm, and they proposed a project called Wilder Ranch and Beaches, which was going to be a community of 35,000 people on what is now Wilder Ranch. Again, it was right at the point where people were beginning to wonder, wow, is that a good thing? What's that going to do to the city? But again, a citizens group got together and decided that wasn't a good idea and made the arguments, and it was never approved, and that is now also protected as a state park. But we came that close in both those situations of having those happen. A West Side story. Raytech, up at the upper end of Schaefer Road, used to be a slaughterhouse. In fact, the cave that we now take our seawater out of was where the wash water from that slaughterhouse with the blood and so forth was discharged. Again, only 35 or so years ago. And if we looked at the Santa Cruz sewer outfall 30 years ago, it was 2,000 feet off West Cliff Drive, and it actually ended in a T that went right straight up, and this was of concern to people that use West Cliff. Now this has been rebuilt. It's right off the Marine Lab. It's about 3 miles off the Marine Lab. We have a new treatment plant. Water quality is good, and we've made a lot of progress. But again, in only a few years, there's been a huge change in our perception of the ocean environment and how we treat it. I also just was going to give you a quick sort of a summary of how this coastline has changed. This is where we're sitting tonight. This was taken back in 1928, the oldest that I know of aerial photographs. This was to be the De Anza Mobile Home Park. This is Natural Bridges State Park. At that time, you can see what was Delaware, and I don't know, what was going on there. Sandy might be up. The railroad grade. So we did have that darn wetland out there then. We have protected that. But somehow it keeps coming back. It was there 75 years ago. So this was to become the Marine Lab property and finally the property we now own. So 1928, there was nothing but farmland. 1943, same location. Here's the property we now own. So this is the De Anza property. In fact, you can see there's natural bridges. They've lost one of the bridges there. But this is to be Natural Bridges Park. But you can see all that was farmed. So this was all agriculture for many, many years. By 1976, you can see the university is getting started up there. I don't know whoever let them in. Sorry. Here's the place where the lab was to be built. It's still in Brussels sprouts. 1978, we're celebrating our 25th anniversary, the very beginnings of the Marine Lab, and I think Bill is here tonight, Bill Doyle, who was really sort of the architect for this early stage of the lab. 84, kept moving in more mobile homes. Those were pretty inexpensive, and we could afford to expand. Actually, the whale that was sitting out there in the field is now beside our first Seymour Center. Many people who haven't been out here for many years can't find the old visitor center and tell them, well, there's another building there now, and we've actually expanded. And today, we have a real, I think, marine science and education center that we can all be very proud of. But it's come a long way in 25 years. You know, what's happening from here? Just to show you that geologic change never really stops. Every time I show this slide and ask people where it is, most people will always say natural bridges, because we're used to seeing natural bridges. But in fact, it's Steamer Lane. So what's happening is the coastline is retreating, arches are collapsing, although here we put a lot of rock in here to stop that from happening. Waldo Ranch, 1900, an arch that people felt comfortable driving across in their horse and buggy. That is subsequently collapsed. In fact, there was another arch over here that is now collapsed. So this is a progressive, ongoing process. This is actually natural bridges. In 1900, there was 1, 2, 3, and I said natural bridges because it's really now Natural Bridge State Park, because we don't have that many bridges. So on the one hand, we can look around and see the coastline is retreating, sea level is rising. That will continue to happen. One of the things I work with on a regular basis is coastal erosion, coastal protection. How do we respond to a constantly changing sea level? Do we build seawalls along the coast? What are their impacts and so forth? And on the sort of positive side, back in 1924, and the docents know this story well, we had this boat that washed up on the sort of wave-cut bench here in front of the Marine Lab. This mast of the La Felice was tilted up against the cliff and was used with a block and tackle to salvage the cargo. That mast is still there 79 years later. So in fact, this stretch of coast in front of the Seymour Center has not changed significantly for 79 years. And when I went into the Coastal Commission trying to get the permit to build this building, I used this for evidence, and we used a 100-foot setback, but I had to promise we would never come in and ask for a seawall. And I thought in all confidence, easy for me to say. So I'm going to leave you with one final thing. What's coming next? From the last 100 million years to the last 100, from the guy who knows it best. This is from our recent trip to China. In fact, this is not a statue of Sandy, but it's of General Joe Stilwell, who we visited while we were in China, and father of Stilwell Hall at Fort Ord. So with that, we'll take a short break and come back to hear our beloved second speaker.